Hey everyone, we're back with unprecedented back-to-back episodes of Going Native. I told you guys at the end of the last episode that we'd see you later this month, and that happens to mean the next day. Now, while you guys shouldn't expect this to be a pattern, we are continuing our excitement in yesterday's release of Visual Studio 2013 Update 4 CTP1, and we wanted to showcase a new feature that's now available in the product. This feature is brought to you by the good folks over in the graphics team, whom you guys met back in episode 27. I had a great interview and demo session with two members of the team, and they are excited to show you guys what they've been working on, so let's get right to it. Hi everyone, welcome to our latest episode of Channel 9 Going Native. My name is Gabriel Ha, behind the camera, and I'm here with some familiar faces.
Hi everyone, my name is Rong Lu, and I'm a program manager on the Visual Studio C++ team. I work on graphics tools for DirectX.
Very cool. And how long have you been at Microsoft?
I've been here for 8 years.
Oh, wow. That's quite a while.
My name is Ian Huff. I'm a developer here. I've done a lot of the dev work on this tool, and I've been a few years on the diagnostics tools, debugger, profiler, and about the last year here on the graphics team.
Very cool. And how long have you been at Microsoft, Ian?
10.
So, Rong, as our program manager, why don't you give us a little preview of what we'll be talking about today?
Yeah, today we're really excited to show you one of the new tools that we just shipped in Visual Studio 2013 Update 4 CTP1. This tool is called GPU Usage. If you're familiar with Visual Studio Performance and Diagnostics Hub, this is one addition to the set of tools that you can use to analyze performance in your application. So the tool we add is going to help collect and analyze GPU usage data for your DirectX applications. And we know that oftentimes there are games or graphics applications that are not hitting target frame rates, like 60 on PC or 30 on a smaller device. You want to understand why your app is running slow, what the problems is in the performance, and how you can improve the performance of your applications. So hopefully this will be a great tool for you to use and understand why your app is running slow and how you can fix that.
And Ian, were you the primary developer who worked on the feature?
Yeah, on the Visual Studio side, yeah.
Okay, very cool. So can you give us sort of a high-level summary of how the tool works?
Yeah, sure. So what we do with this tool is we deploy it out, and it collects ETW data on the box wherever the game is running. And on that device, we collect a few things. We collect context switch information that lets us see what applications are doing what on the CPU on the time. We also collect DMA packet information. What this is, and this has been around before, is that it can tell us when the GPU is executing work. But what we couldn't tell you before this work is we couldn't say what that work was. We just knew the GPU was busy doing something. What we've added now is we've merged those two things together, and we've also added in the data we know within each chunk of work that the GPU does. We can say, okay, this was a draw index call, here's how long it took. This was a clear render target, here's how long that took. So adding in that information gives us kind of a rich story to say, hey, here's what was actually going on both sides of the equation.
All right, so I hear you guys have a demo for us?
Yeah, we do.
Cool.
Let's get to it.
All right.
Okay, now let's see a demo of this new tool. What I have here is a DirectX application open, and I am running Visual Studio 2013 Update 4 CTP1 bits, which you guys can download from the web as well. So what I'm going to do here is I'm going to launch the GPU usage tool through the Performance and Diagnostics Hub, where you can find multiple tools that you can use to diagnose performance issues in your application. In this case, we are going to run the new GPU usage tool along with the existing CPU usage tool. This will allow us to collect information from both the CPU and the GPU to get an idea of whether this app is CPU bound or GPU bound. Go back to VS. First thing I will show you is the swim lanes that we have added to Visual Studio. Now notice that while this app is running, we are showing you real-time frame time for each frame, your frames per second, the threshold that's marking 60, which will be the target. Of course, you can change that to 30 if you want. And in addition to those, we also have added a GPU utilization swim lane. This is telling you how busy your GPU is. And in addition to that, there's also a CPU utilization lane. This is actually coming from the CPU usage tool. The good thing is, since we're running both at the same time, you get to see both CPU and GPU utilizations at the same time. Notice that this is running about 60 frames per second. Now we're going to stop the app and look at the report that this is going to generate for us and understand why this app is not hitting 60 frames per second and whether this app is CPU or GPU bound, and see what we can do about it. Here's the report that gets generated. Let's go back and look at the frame rate. This is apparently below 60 frames per second. Here you can look at the whole session if you want, but if there are specific range in the session that you want to drill into, you can also select the range anywhere in this session and go and look at details of the GPU usage to understand what's going on there. So now we are opening a separate window for the GPU usage data. Zoom a little bit. So basically what we are collecting is a list of GPU events that actually occurred on the GPU. We get that data back from the GPU driver. And as you step through all these events, you will actually see these events marked on GPU lanes and CPU lanes. This machine has 4 CPU cores. That's why you see 4 different lanes. And we have separate lanes for each GPU engine. In this case, you can see this dual index instanced event happened here on the GPU, and its corresponding CPU work is also marked. This is telling us this is when the corresponding CPU work happened. As you step through this event list, you also see some of the events are actually grouped. These groupings are coming from markers that we inserted into the app using the 3D interface, user-defined annotations. This can be really useful if you have a fairly complex application. And if you don't have those markers, you'll basically get a flat list of events, and that would be pretty hard to relate back to where the code is. Now, by using these group markers to group events, you will be able to say, okay, this draw city is where it's slow on the GPU, and you will be able to relate back to find where your code is. Okay, now let's take a look at the data here and try to figure out why this app is slow. Now, first of all, look at all these vsync lines. These are the gray lines that's marking all the vsyncs from the monitor. For your app to hit 60 frames per second, basically you need to do 1% between every 2 vsync lines. Like this one is hitting this vsync, but if we go and look at next %, it's actually happening after the second vsync, which means this % missed the second vsync. This is why this app is not running at 60 frames per second. Now the next thing we're going to look at is trying to understand whether this app is CPU bound or GPU bound. We noticed that a lot of events happened on the GPU to draw city, which is apparently taking a long time on the GPU. So this could be something we should optimize on the GPU side if you want to make it faster. But really what the problem is with this app, if we look closer, is although this is taking long, but still would fit within 2 vsyncs. This is taking 12 milliseconds, while you have about 16 milliseconds between 2 vsyncs. So this will still fit. But why is this app not hitting 60 frames per second? Let's take a look at draw ring, which is the next section of draw calls after drawing the city. You'll see that on the GPU lane, it spent not very long to draw the rings, but if you go back and look at the CPU lane, the CPU is preparing the data for the ring. This actually happened long before the GPU is ready to render anything. This basically means the CPU spent a bunch of time preparing the data for all the ring jobs before the GPU started to render. So there's definitely a CPU bound problem in this app. And the other thing to notice is that although the CPU has a lot of work to do, only one CPU core is busy at one time. And while this core is busy doing things, all the other CPU cores seems to be free. So one thing we could try to optimize this app for is by offloading the work to multiple CPU lanes, so the CPU don't have to wait that long before it can start rendering.
Rong's showing just a really good way of showing how we expect people to use this tool the first time. You start on the top level, you see those swim lanes, you can see that red line that's drawn across them, and you can say, okay, so I'm below my target. This is the view kind of that you expect to say, hey, do I even have a problem or not? But if you're not making your target, then you have to move into a section of the details. Maybe you pick a spot where your usage looked high, or you pick a spot where the frame rate spike. Maybe with something like this is just kind of bad in general, and you start looking into it. And then from in there, you have to look at your 2 resources, your CPU and your GPU, and you've got to just kind of decide, hey, what am I essentially running out of, right? I mean, if your GPU lane has spaces in it, you have time where the GPU is sitting around doing nothing. If you have space in your CPU lanes, you know there's times where the CPU is sitting around doing nothing, and then you kind of look at your best way to optimize between those ones. And the example we show here, there is GPU time that you could optimize, but from our investigation here, we see it's just using one core all the time on the CPU, and that's causing some slowdowns.
Right. One more thing to add is all these different colors that we use to represent different processes. We capture data from all the processes who have used the GPU resource in the session. And each process was assigned a different color. That's why you see different colors in here. And the one we're looking at right now is the one we started tool with, which is City Demo XE, which is the green bars.
Also, we talked a bit about the presents and the vsyncs too. And one of the things you can do if you're trying to look at these, we have a filter box up top. And if you type present into there, what you'll get then in the list below is you'll get just a flat list of all the present calls that were made. And if you flip down through those, if you just click on one and then kind of move down, you can see each one of them, and you can see if they're hitting the vsyncs in a really easy fashion, right? So if you see one of these in every chunk of time, you're running at 60 frames a second. If you see it every two of them, you're running at 30 frames per second. You see it less, then your frame rate's getting worse and worse. So that's kind of a quick way to say, hey, am I actually making it? See, this one is making it, but then some of the next one is pushed off to another one. The next one missed the next vsync. So you can actually see these problems. That's a good quick way to see it.
So now we know there is a potential CPU-bound problem in these applications. Let's go back to the DAG session file, and let's switch to look at the details of the CPU usage. Good that we run both tools at the same time, so we can get to both details of the CPU and GPU in the same session without having to rerun the tool. Okay, here's the CPU usage data. Now, it basically can tell me which function is taking how much of my CPU resources. So in this case, let's try to drill into this node that seems to take 98% of my CPU resource. And then keep drilling here. This is the lambda. Oh, still 94%. Okay, here's my code. Seems like this is my city demo. And looks like this is taking 94%. Oh, here's my render loop. Demo renderer, and then we can keep drilling in here. Now here tells us where my CPU resource is being used. So here's the render call to draw my raindrops. Here's the render call to draw my city. And we already know from the other view that draw city is not taking long on the CPU, while draw rain is. So let's drill in that a little bit more. And here's the commit updates, which is actually the function that's making all the updates. Now we can go and say view source, which is going to take me back to my source code. So here's my commit updates. That's taking over 60% of my CPU time. And let's try to walk through this code and see why it is slow. This is just if and start initialize my instance list. So each of my raindrop is going to be an instance in this list. So basically what this is doing is it's a for loop that's iterating this whole list, trying to prepare the data for each raindrop. So I am actually drawing 5,000 raindrops in this app. So this is basically a for loop of 5,000 times, which can be pretty slow. In this case, it is. So one quick way we can optimize this is to parallelize this task. So because it's a for loop, that's apparently something that we can use parallel for instead of for loop. So what I have here, I'm gonna uncomment that, and I'm gonna comment out this. So this is basically doing the same thing. The only difference is instead of doing for loop, I am using parallel for, which is a library that we ship with Visual Studio. This is going to automatically create different tasks using multiple cores, and I don't have to worry about anything else. I just need to switch from for to parallel for. Now that's done, and let's run this tool again on this app and see if we have actually made any improvements. What is that?
56.
Still, I should hit 60. Something else is using my GPU resources. This is a challenge with demo anything graphics. Can't TSing, can't have anything running in the background, can't use software simulation. We rerun the app and we recollected all the data. Now let's take a look at these graphs. First of all, the frame rate is apparently hitting 60 frames per second. It's hitting the threshold here. And if we look at GPU usage and CPU usage data, we can tell that CPU is now a lot more busy. Apparently multiple cores are being utilized. And on GPU side, the GPU is doing a lot more work as well, because now it has to constantly present all the frames 60 times per second. This is apparently looking a lot better than it used to.
And if we want, we can take a look and zoom in on one section, see how that looks.
Good idea. Let's select section and then drill into the details. Oh, here's a much more busy CPU lane.
If you zoom out too, you can look at the previous run. You can see how spaced out all the green is. A lot of other things are happening. The GPU has a bunch of big empty ones. And now in this one, it looks much more dense, which is what you want to see when you're running a game. It's busy. The CPU is busy, the GPU is busy, and everyone's working.
Yeah, it looks like the GPU is hitting, all the presents are hitting every single VSync. So this app was running at 60 frames per second, and all the CPU cores on this machine are being utilized. They're all doing work at the same time.
And if you get issues still here with your GPU, for instance, in this case, what you might want to do is you could sort by your most expensive draw calls. You could sort by draw indexed instance, and you could see, hey, maybe some of the things I'm using for geometry are just too big. But right now, everything fits, so it looks good.
Yeah, this is how you can use the tool to tell whether it's CPU bound or GPU bound, and hopefully get some idea of how to fix the problem. So yeah, this is the new tool we were talking about. Hopefully you will find this useful, and I would really encourage you to try out this new tool. If you haven't already, download Visual Studio 2013 Update 4 CTP1, try it out, and let us know how this works for you.
Rong, Ian, thank you guys so much for your time. I really hope customers will look forward to using this.
Thank you for having us.
Yeah,
Thank you for watching.
That's our episode for today. As always, be sure to check out the links in the description and leave us something in the comments below. In other news, I have been searching for another co-host to join me on the show, but I wanted to mention that the reason I still use the inclusive we when I address you guys is because there are a lot of people who work behind the scenes to help make these episodes happen, especially in terms of finding people who are working on great stuff for us to showcase. So, as always, thank you for watching, and maybe you'll see someone with me next month.